So this video is another addendum to the first week of lectures for Cal 1, December 2020, section 04T. Basically, the first day we ended early. I made a mistake with the time. I'm just so accustomed to classes ending at the 50-minute mark, not the 15-minute mark. So this will be about 20-25 minutes of additional examples. And either it'll be posted Thursday evening or Friday morning. I'm not sure yet when it will be available. But of course, if you're hearing this, then you already know that. Anyway, so we left off last time doing, we had just done the properties of limits, and we did couple of examples, right? We listed all the properties, did a few examples, and I alluded to something that we're not going to have to go through all of this trouble every time, that there's some shortcuts we can take. We're basically implicitly using the properties rather than explicitly writing them out. There's a shorter way to do that. So basically, the limits of polynomial and rational functions are relatively easy. So if, say, p of x is a polynomial function, then the limit can be obtained by just, or not the limit, but a limit can be obtained just by plugging in the value that x is approaching. So if I say the limit as x goes to a of p of x, that will just equal p of a, right? If we back up to example we did before, here, if I just plug 3 in, that's effectively what I got. I was applying the sum rule, the constant multiple rule, the identity rule, and the constant rule, and that's what I achieved. So why don't we just do that, right? Similarly, in this example, if I had just plugged in 2 into every instantiation of x, every instance of x, then I would get the same result. I would go, is it 13 over 9? 13 over 9. I would get that right result. I could skip all of this writing. That's just how it's going to work out. So if, and there's a couple ways to phrase this. Let's say if q of x is a rational function, then, well, there's really two things. I'm kind of running out of room. Let's say this. Then q of x equals some numerator function divided by some denominator function, where both n and d, these are both polynomials. Right? And the limit as x approaches a of q of x equals q of a, which of course this is n of a over d of a. The numerator evaluated a divided by the denominator evaluated a. Of course, only if d of a is not equal to 0, because of course you can't divide by 0, right? So if plugging into a rational function, plugging in a, doesn't result in division by 0, then go ahead and do it, and you'll get the right result that way. So for polynomials and rational functions, it's always going to work that way. So this example, I can just plug in 2 and see what I get. If I end up getting 0 on bottom, that means, oh, this doesn't work. But it's something I can try, right? So in this case, if I plug in 2, I'll have, was that 3 times 8, so 24, minus 2 plus 5, all over 4 plus 2 minus 2. So that'll be, was that 27 over 4? Oops. Yeah, 27 over 4. I'm done. I didn't have to do any algebra, didn't have to do anything, just no rearrangements with these properties. Now, I'm implicitly using them, but we don't have to write it out that way every time. Okay. There is a general strategy in the OpenStax textbook on page 164. You should probably go read that. I'm basically going to be doing that, and I'll talk about my reasoning as I go through. Like with this one, I try plugging in, and if it works, great. And if it doesn't, we'll have to try something else. So I'm going to be implementing this strategy, but you should go to the textbook just to read. It's pretty short. It's like a third of a page or a quarter of a page. I just don't want to write it out here when it's already in print. So This is one of the earliest examples, maybe even the first example that we dealt with, where if I plug in, now I'm not going to say I'm not going to say equals because I know how this is going to go. Let's say I'm going to put in, let's do this. Let's say equals. All right, well, if I plug in, I'll have 2 squared minus 4 or 2 minus 2. Oh, that equals 0 over 0, right? That means that there's an indeterminate form. So that means that this is not equal. So it's okay to write this because you're checking it out. You're trying to see if plugging gives you the result, but it doesn't. So I'm going to cross out this equal sign. It's not equal, and I don't want to make it look like I think it's equal, right? I get an indeterminate form that way. So it's important on any written work. If you start out by saying, oh, this equals and plugging in, and you find out, no, it doesn't, go cross that out, okay? So I have to do something else instead. I need to use some algebra. So this is something that we could have done earlier with that first example. Basically, one way to present the concept is to take this example here and look at it numerically, look at it graphically, and look at it algebraically, and do every version to sort of give a microcosm of the entire chapter. But I decided, no, let's just defer the algebraic approach until later when we actually get into more of the algebraic approach. So what I'm going to do is, when you have a rational function and plugging in gives you 0 over 0, there's something called the factor remainder theorem that you might remember from algebra. Basically, if plugging in a number, say a or 2, let's say plugging in 2 causes a polynomial to total up to 0, that means that 2 is a root of the polynomial, and then that polynomial must factor as something times x minus 2, right? So I know, well, the bottom is just x minus 2, but I know the top has to factor as something. This guy has to factor as something, question mark, times x minus 2. That's from the factor remainder theorem, okay? Now, this one's relatively easy. That's why I chose it. X squared minus 4 is a difference of squares. So this factors as x minus 2 times x plus 2 all over x minus 2. And now I can cancel. The x minus 2 here and the x minus 2 here can go away. And so this equals the limit as x goes to 2 of x plus 2. When you cancel in a limit like this, the limit value is maintained. It doesn't change. And now I can say, oh, well, now I have a limit of a polynomial. Now I can just plug it in, and I get 2 plus 2 is 4, which, of course, that's what we calculated previously when we were using a numerical table. We got 4. So I generally don't need to resort to doing numerical tables. Sometimes it might seem easier or more expedient, but it's often really tedious, especially if you're doing it by hand. It's super tedious. If you had like an Excel spreadsheet, yeah, well, you could probably, if you can get Excel to accept the formula, then yeah, okay. Then you could use a spreadsheet, but we don't need to do that. We just do a little bit of algebra, cancel, factor, cancel, and we're done. And this one's relatively easy. We'll have some, as we go along, they're a little bit more complicated. So we have this problem, and it's a little bit more complicated than the one we had up here because, again, the top is a cubic function, the bottom is a quartic function. So I'm going to try plugging in to see what happens with that. This probably is what you should start with because maybe, sometimes plugging in just gets you the result and you're done. You don't have to do any algebra. Okay, so in the top I'll have a negative 8 plus 8. In the bottom I'll have 16 minus 16, right? Oh, well, that's 0 over 0. That's bad, right? Well, not bad. It's just that we're not done, which I guess you could say is a bad thing. So that's just not what it is. So I'm going to make sure to cross out that equal sign because that's not it. I have to factor. So the denominator, you might see how to factor this one. This one's easier, even though the degree is higher. You might say, well, if the degree is higher, shouldn't it be harder? Well, not necessarily. In this case, this is a difference of squares, right? This is going to factor as x squared minus 4 times x squared plus 4. The numerator, this one's a little bit harder. You might not be familiar with how a sum of cubes factors, because 8 is 2 cubed. But this is going to factor as x plus 2 times x squared minus 2x plus 4, as I recall. So this equals the limit as x goes to negative 2. And the top will factor as x plus 2. And there's a formula for this. I can show you the formula in a few minutes, or in a minute or two. So x squared minus 2x plus 4. And if you take the time to FOIL this out, or really use the distributive property, you'll get x cubed plus 8 if you check this out. Basically, these two make minus 2x. Sorry. Minus 4x, and these two make 4x. And then they cancel. And then you can check the other terms. There's cancellation. You get x cubed plus 8. Okay, so the bottom, this factors as x squared minus 2 times x squared plus 2. Okay. Now we're not done factoring because I'm not able to cancel anything yet. Like this this factor does not cancel with this factor, right? Because they're not identical. They would have to be identical. Oh, I have a mistake. My mistake. Those are 4s. I'm sorry. 4s, right? 4 times 4 is 16, right? Okay. And again, nothing can cancel yet. But this guy, this is still a difference of squares, so I can factor it again. So this is equal to the limit as x goes to -2 times x plus 2 times x squared minus, not 4, 2x plus 4, all over x plus 2x minus 2x squared plus 4. And now I can cancel the x plus 2. These are the factors that were causing the zeros to show up. Because when you plug in -2 to x plus 2, you get 0. Right? If I were to go plug in -2 now, -2 plus 2 is 0. -2 plus 2 is 0. But since I'm crossing those out, I'm left with the non-zero part. Okay? And this is, again, I knew this would happen because of the factor remainder theorem. Because I got this, I know this is going to happen if I factor correctly. Okay. Oh yeah, sorry, I need to cross those out. Okay. So this is equal to the limit as x goes to -2 times, not times of, x squared minus 2x plus 4 over. And if I really wanted to, if I had a reason to do it, I could FOIL these together again. I don't need to, but I could if I wanted to. Then x minus 2 times x squared plus 4. Okay, running short on room, but we're almost done. So now I can plug in. As long as plugging in doesn't create division by 0, I can go ahead and do that. This will be 4 plus 4 plus 4. -2 squared is 4, and -2 times -2 is 4. All over -4 times, is that 8? I think it's 8, yeah. So this will come up here, since I'm running out of room. This will be 12 over -32, which that reduces to 3 over -8. So 3 over -8 is the result we get, or if you want, -3/8. And unless we've made a mistake, which I don't believe we have. I'm pretty sure that this is correct. Unless we've made a mistake, then there we go. That's the result. That's the limit. So if I want to go, I'm not going to go back up and write up here, although I could if I wanted to. Okay. Anyway, that's that example. Quite a bit of algebra. We had to do a lot of factoring, but that's because the bottom was degree 4, the top is degree 3. So what are those formulas? I said that there are some formulas for this. I don't want them out of order. Let's do this. Let's just push this down a bit. We can always just push down the next thing as well. So whenever you have a sum of cubes, if you have a cubed plus b cubed, this is always going to be a plus b. Well, you know what? Let's do this. Let's do the familiar one first. A squared minus b squared. This is always going to factor as a minus b times a plus b. That's one that you probably know, because you've probably seen it enough. A squared plus b squared does not factor, but unless you want to use complex numbers, and we're not using complex numbers in Cal 1. So it just doesn't factor. Now, sum of cubes does. So a plus b times a squared minus a b plus b squared. Okay? Which, that's how I got x squared, because x was a was x, and then 2 times x plus 2 squared, because b is 2 in this case. Okay, and then also a difference of cubes also factors. So a minus b times a squared plus ab plus b cubed. I believe that's correct. And you can check these by foiling. If you foil this out, you get a cubed plus b cubed. And if you foil this out, you get a cubed minus b cubed. I'm pretty sure. Yeah, that's right. Okay. Okay. So next example. And I guess I will push that down. We'll just, as we go along, we'll push them down. Okay, so we're running up on about 18 minutes here. Now, I am going to clip out an error I made earlier, and I'll probably clip out what I'm saying right now, actually. But we're probably going to do 2 more examples in this video. Okay, so for this one, if I plug in 1, right, I'll get 1 over 1 minus 1 over 1 minus 1. Oh, that's 0 over 0. That means that that's not what that is. Cross it out, right? This means we have to do some algebra. So what I'm going to do with this one is I'm going to, well, first I'll rewrite it. There's 2 basic ways to deal with this. And I'm going to show the way that it seems more straightforward to me. I prefer it. So I'm going to multiply top and bottom by x because I want to cancel out this x here, okay? And you'll see why this ends up working. So this is going to equal, I'm trying to conserve space, so I'll just put it here. So when I distribute, this x will apply to that. I'll have x. If I want, I can say I have x over x, so which is 1. Of course, a number times its reciprocal is always 1 anyway. And then when I distribute here, I'll just have x. This one, when I distribute here, I'll have x squared. When I distribute here, I'll have just x. And again, I'm multiplying by x over x, which is really just 1, so I'm not really changing anything. I'm just manipulating the algebra. So I'll have 1 minus x over, and in fact, the bottom I'm not going to distribute. I'm going to leave it written like that, factored. Now notice that this bottom, this top are not quite the same. The order is different. So I'm going to, there's a couple ways to say this. I'm going to take the numerator and factor out a negative 1. So this is equal to limit x goes to 1. In the top, I'll have negative x minus 1 over x minus 1 times x. Now, since those are identical, I can cancel. And so, let me rephrase this. The factor that creates the zeros is going to go away. Right? If I plug in 1 into those 2 factors in parentheses, they both become zeros. That's why the indeterminate form showed up. So by doing this factorization and then canceling, I'm removing those extra zeros that don't really need to be there. Or in fact, for my purposes, I want to find the limit. They shouldn't be there. So I get the limit as x goes to 1 of negative 1 over x, and you plug in 1, you get negative 1. So there's our result. Okay, so that's that example. I think we have time for one more. Yeah, we definitely have time for this one, I think. This one, perhaps not. This one's a bit lengthier. Okay, so this example, if I could say, well, the root property tells me that as long as I don't end up with the even root of a negative, I just go ahead and do it. So I can just plug this in. I get the square root of a 0. Ah, bam, 0, done, right? Well, kind of. There's a caveat here. So basically, up here in those properties, so this actually, this really, let's make an amendment. Let's say not or equal to, because if L equals 0, there's an exception. So at the time it made sense, right? The even root of 0, the square root of 0 is 0. But let's look at what issue arises. Sometimes you have to give the broad properties and then dig down to the details later. I'm going to say that this is incorrect. Now we'll look at why. Why is that? Well, if I go and I look at the limit from, say, the left, as x goes to 2 from the left, of the square root of 2 minus x, right? So when we're doing this, since x is going to 2 from the left, x is less than 2, right? So if I subtract x on both sides, 0 is less than 2 minus x. So 2 minus x is positive. Oh, I have a root of a positive number. What this means is, another way of phrasing this is that let's do it this way. The domain of that function, the square root of 2 minus x, is 2 to infinity. You can't plug, is that right? Hold on. Let's reverse that. Negative infinity to 2. You can't plug in 3 or 4 or 5 because then you'd have a root of a negative. It just doesn't work, right? So when we're approaching 2 from below or from the left, I'm plugging in smaller numbers. I'm getting the square root of a positive number. So that works out, and I do get 0 that way. That works. Just plug it in, you get 0. However, if I go look at the right limit, the limit is x goes to 2 from the right. Okay? Well, the square root of 2 minus x. Remember, the domain of that function is negative infinity to 2. So if x is going to 2 from the right, it's going to be like 4, 3, 2.5, 2.1, 2.01. Those aren't in the domain of the function. So how would you evaluate the function behavior? Remember, the entirety of the limit concept, or 99% of the limit concept, is what is the behavior of the function when the input is close to the number we care about? Okay, what's the behavior nearby? Well, when x goes to 2 from the right, there's no behavior. It doesn't exist because the domain doesn't include those input values. So because x is greater than 2, that means that 2 minus x is negative. It doesn't work. You can't plug that into the function, so this does not exist. Okay? So we come back to this. Some books will say this might seem it might seem odd what I'm about to describe it. Some books will say that this limit is 0, and some books will say this limit does not exist. Okay? I'm really just pointing out a caveat that, well, depending on what you're using this for, especially if you take higher level math courses later, they might say in this context we're going to treat it differently. It might seem like, well, hold on a second. Whoa, you can't just change the rules of math. You can't have one class does the rules this way and another class does the rules the other way. Well, actually, you totally can. Just I know I'm running over on time a little bit, but when I was in kindergarten, I remember learning subtraction, and teachers, okay, what's 5 minus 2? And we're supposed to say 3, and I asked, well, what about 2 minus 5? And the teacher said, oh, no, 5's too big to be subtracted from 2. Right? Think about that. 5 is too big to be subtracted from 2. That's because we hadn't covered negative numbers yet. She didn't want to have to explain 10 things on day 1. You explain one thing on day 1, you explain the next thing on day 2, right? You can't, in a classroom where you're trying to corral 20 kids, you can't just give everything all at once. It's not going to work, right? So we're going to say, you know what? For our purposes, we are not going to worry about the right-hand limit because that's not in the domain of the function. So we'll say, you know what? We will go ahead and accept this reasoning as fine. That's okay, but we have to understand this context. If I didn't tell you this context and just said go forward with this, that would be a little improper because then you don't know the technicality of why that's okay. Why is it that we do get 0? But if you understand this, then you know why we do get 0, because although the right limit doesn't exist, we're not going to require a function whose domain doesn't include those values to be considered for that right-hand limit. Like, why would you consider it? That's not in the domain. So just something to be aware of. Some books will say the limit does not exist. I'm sorry, the two-sided limit does not exist, but that the one-sided limit does. Okay. Some books will go with this, and the book that we're using does go with this. That's why when I gave this property earlier, here, let me find it. Yep. That's why the book said, oh, if L or if n is even, L must be greater than or equal to 0. So we're going to go back and say, you know what? Let's accept the book's the book's determination. That yes, that does work. We will accept what the book says. I just wanted to, if I don't clarify that for you, you might run into trouble later on, especially if you go look at Paul's notes online, he might handle it differently. Or if you go look up a YouTube video or something, it might get handled differently. So we're going to accept this version, but I felt like I had to let you know that there are two versions of that. Some books do it one way, other books do it another way. Anyway, we did most of the examples I wanted to do. This example cannot be done in like 2 or 3 minutes, and we're already at about 28. So let's stop it there. So I'll stop the video there, and yeah. So basically, after you watch this video, I mean, if you're hearing this, you've already watched it, so I guess that's not relevant. So I guess I'll stop the video here.